work that we've been doing at our lab. So to kind of jump right in, I don't ever want to assume that people know the difference between sort of air traffic control and air traffic management. Okay. So the way that I'm going to try to make this difference clear is just through one video focused on Dallas Airport. So this is a very large airport in the US, located in Texas. And what you're going to see in the next slide, and I'll keep it paused for now, but basically, so here is Dallas. This is where Dallas is. And all of the green stuff, that's bad weather. Okay, so pilots don't really want to fly through those. You're going to pay particular attention to the red airplanes. So these red planes are all arrivals into Dallas Fort Worth. Okay. The job of air traffic management is to basically say, well, these, because of weather, the arrival capacity, so number of aircraft that can land at Dallas is lowered. So less capacity at Dallas. To manage the traffic, what we want to be sure is that the demand going into Dallas is about the same as the capacity of Dallas. Okay. Um, if air traffic management doesn't do their jobs quite as nicely, we get situations like what we're going to see in this video where um, we see this weather growing and growing and growing, and we see air traffic control. So now this is not air traffic management, this is air traffic control. Try to vector or try to move all of these aircraft safely into Dallas. But at some point, the weather grows way too big and way too out of control. And what we start seeing is we start seeing holding patterns appear. Okay. So airplanes start waiting at the boundaries of the Dallas airspace in order for this weather to move past Dallas. Okay. So air traffic management's entire job is to ensure that capacity and demand is balanced such that this situation doesn't occur or it doesn't occur as often. Okay. Air traffic control is responsible for kind of real-time separation of flights. So I always like to think of air traffic management as like, when you drive your car, maybe it's you deciding to take a different route or you deciding to pay a toll and go on a expressway, whereas air traffic control is individual vehicles. How do I make sure that they don't crash into each other? Okay. So this is going to be a talk mostly about air traffic management, not on the control side. Okay. Specifically, I'm going to talk to you about some of the new work that we've been doing to help air traffic managers deal with situations like this one. Okay, that's the first main storyline. The second main storyline is actually more of a broader story about living in a society where machine learning supports a lot of our decision making. So the second storyline is kind of more about how do we make optimal decisions when machine learning might be wrong. Okay. So that's really kind of the two main storylines for today. I will first walk through kind of more of the air traffic management side so that you have a bit of context for what I'll be talking to you about. So let's think about, let's say, a flight into Seoul Incheon. Okay, what is one of the main determinants of whether or not that flight will be on time? It's the arrival capacity at Seoul Incheon. So how many airplanes can Seoul land safely in an hour? Okay. One of the principal determining factors of how many aircraft can arrive in an hour is what's called the prevailing runway configuration. So it's basically which runways am I using for which runways am I using for departures and which runways am I using for arrivals. This is my hometown airport. This is DTW, Detroit. As some of you may know, airplanes like to land and take off into the wind. So they want the wind blowing at their nose. Okay. So this is what's called the south flow configuration at DTW. So the wind is blowing from south to north, and so we land and take off this way. So these two runways are being used for arrivals. This runway is being used for mixed operations, arrivals and departures, and this runway is being used for departures. When Detroit is on this configuration, Detroit can land about 100 flights per hour. Okay, that's the capacity of Detroit Airport. In weirder times, more weird situations, when we have east-west winds. So east-west winds are not very common in where DTW is located. But when we have east-west winds, we have to use these two runways for both departures and arrivals. And then the arrival capacity of Detroit drops to about 40. Okay, so we go from 100 to about 40 aircraft per hour. Now, of course, this is such a well-studied problem at this point, this problem of predicting the runway configuration. So imagine you had a machine learning model. Okay. It, you can give me your favorite machine learning model for this problem. It could be a neural network, it could be a random forest classifier, whatever is your favorite machine learning model. That machine learning model is going to take in weather, wind speed, wind conditions, forecasts, and so on, and it's going to output the predicted runway configuration for that airport. Very well studied problem. We've looked at this problem probably for the last 10, 20, not me specifically, but like people have looked at this problem for quite a while. Okay. In fact, it's such a mature problem that it's been taken up by industry. Maybe some of you have heard of FlightAware. Basically, it's like a flight tracking website. FlightAware has actually been purchased by Collins Aerospace, and they have a product called FlightAware Foresight. You can Google it right now, and you can play around with it. It's actually kind of fun. This is a screenshot from FlightAware Foresight. One of the tools they have is the arrival runway predictor. You can put in a flight. So actually, I did this when I was in flight. I was flying from Boston to Detroit. This is a couple years ago at this point. But I was flying from Boston to Detroit on Delta 2222. And you can actually see what is the predicted arrival runway for this aircraft. Okay. So the output of this black box machine learning algorithm, again, it's black boxes. I don't know what FlightAware and Collins Aerospace is using. Okay. I know it's a machine learning model. I can see the outputs, right? The outputs, so what is the output here? The output of course is a probability mass function over the possible arrival runways. Okay. In this case, this is a very boring prediction, right? It's basically extremely certain that I'm going to land on 21 left. Okay. Again, this is not very surprising because if you look, there's no weather on this day. So Detroit is in an optimal configuration, and they thought that I was going to land on this runway. This is 21 left here. And I did. Okay. So a very boring, boring prediction. This is not very interesting. This is a day where you can probably trust machine learning because it seems like it's doing quite well. Okay. Not a very hard day for air traffic management. Okay, let me give you a different flight. So this is the flight. This is actually Korean Air 401 from Seoul to Sydney. Okay. And now what's interesting here is if you look at the output of this machine learning model, at first it's very confident, okay, that we're going to land on 16 right. And to give you a brief lesson on how runways are named, the number of the runway is basically the dominant magnetic heading that your nose points in if you're landing on that runway. So runway 16 will point in the direction of 160 degrees in magnetic heading. Okay, so this is a south facing configuration. Okay. But as we, this is a pretty confident prediction several hours before landing. But then as we get closer and closer to landing, we see that there starts to be a little bit of a divergence. Okay, there starts to become this likelihood of also landing on 34 right. So 34 is going to be north facing, right? It's 340 degrees magnetic heading. So this tells me as an air traffic manager, if I were in my air traffic managing shoes, this would tell me that I actually don't have a lot of confidence in my weather forecasts because I don't know if it's going to be a southern wind or a northern wind. Okay. And of course, we still kind of have a bit of uncertainty even at the most recent time of querying this machine learning model. Okay. So there's two types of uncertainties that I want to kind of make you aware of here. So if you slice this diagram vertically, so you fix a timestamp and you look vertically, that's kind of the typical uncertainties that hopefully all of us are used to thinking about when it comes to machine learning. Okay. Machine learning never gives you a deterministic answer, right? Machine learning, when it gives you a prediction, it is by definition a probabilistic prediction. Okay. If the machine learning is just giving you one number, it's probably a mean or it's probably an expectation, right? It's some summary statistic on the output probability mass function or probability distribution function. But clearly, if you look horizontally, there's also distribution shifts going on here. Okay, so what I'm trying to get you to be convinced of is that not only is there uncertainty in the outcome of the machine learning model, the output of the machine learning model, but that output, which is already uncertain, has kind of this double layer of uncertainty around it. Maybe the machine learning is predicting that your arrival capacity is 20 aircraft per hour. Is a Gaussian distribution centered at 20 aircraft per hour, but in reality, it was a bimodal distribution, right? So in that case, that would be a distribution mis-specification, right? Or in reality, it was a Gaussian distribution centered at 10 aircraft per hour, in which case it would be a mean shift, right? Or maybe you got the variance wrong, right? So you could it's not enough to try to make decisions based on, so you get this output from the machine learning model and you say, okay, there's uncertainty in this model. That's fine. Maybe I know how to make decisions against that. Maybe you use stochastic optimization and so on. But this is clearly showing me that maybe that distribution could be wrong, that there could be distributional errors and distributional uncertainty. Okay, so the question is, how do we do air traffic management in this wild, wild world? Okay, so keep this in mind while we go back to air traffic management a little bit. And we'll basically, this will let me kind of introduce the math. As I said, one of the principal jobs of the air traffic manager is to manage the balance between demand and capacity. Okay. What we don't want to have happen is Seoul has an arrival capacity problem. Maybe there's bad weather, maybe there's, aircraft emergency. Something has degraded the arrival capacity at Seoul Incheon. Okay. If we know that the arrival capacity will be decreased for the next 3 hours, we may want to assign some proactive delays to flights so that they don't take off, come to Seoul, realize they cannot land, and then have to do holding, right? You can't just stop the aircraft, right? It basically needs to hold, right? And that's very expensive. Okay, doing this, imagine doing 1 hour of airborne holding versus 1 hour of waiting on the ground at your origin airport, engines off, at the gates. Which one is more expensive? So hopefully it's clear that the one where you're holding is going to be far more expensive. So rule of thumb, not super precise, but 1 minute, if 1 minute of ground delay is $1, 1 minute of airborne delay is $3 to $5. Okay, so it's a significant cost for the airlines. Okay. And of course, we're not even diving into the environmental impacts, right? Using more fuel and so on. So this is actually a principal control, a principal management strategy that we use in air transportation. So here I'm plotting each bar is a single day in 2019, and the height of the bar is the amount of delay minutes. Blue means delay taken on the ground, and red means delay taken in the air. Okay, so clearly we do a pretty good job of managing um, to shove delays into the ground side. Okay. This also happens, although to a lower extent in the Asia region, because it's basically hard to coordinate across countries, right? So, in Seoul, yes, you have you have some domestic flights, but most of your flights are like coming from Singapore, coming from Indonesia, right? Coming from all these different countries. So there's sort of a coordination cost for basically letting another country know, hey, by the way, we have a arrival capacity issue, stay where you are until we figure ourselves out. So as a researcher, when I see this, I ask myself two questions. The first question is, how do we turn more red into blue? Okay, so how do we turn more airborne delay into ground delay? That's the first question. The second question is, which is more relevant for us passengers, how do I reduce the height of the bars in general, right? So how do I reduce delay in this system? I'm going to say something controversial, perhaps, but hopefully you'll agree with me. Some delay is not bad. If you tell me Seoul Incheon never has flight delays, I wouldn't be very impressed because I would say, oh, maybe you overbuilt Seoul Incheon. Maybe you overbuilt Seoul Incheon so that it can handle 400 aircraft per hour, but you only have the demand for 100. So of course you won't get delays, right? But did you need to spend that money? Right? Like, is this a worthwhile investment? So some delay is not bad. I think some delay is a sign that you are using your capacity to its design amount. Okay. And if any of you have done a little bit of queuing theory, you'll know that as the service rate approaches the arrival rate into a queue, you do get sort of increase in the average expected waiting time. Because you basically get these jitters where sometimes the demand does exceed capacity a little bit and you get a little bit of delay. So some delay is not bad. What I want to get rid of is excess delay. Okay, so keep these two questions in mind. I want to take airborne delay and shove it into ground delay, and I want to get rid of excess delay. How do we reconcile these two things? The way that I want you to think about it is almost as like a two-phase cost structure. Okay. What are these two phases? The first phase is you are overly aggressive. What do I mean by that? Hey, I know Seoul Incheon will have a problem. Don't worry about it. Just go. Like, just depart. Okay. That's overly aggressive. You will have zero ground delay, but you'll have a lot of airborne delay potentially because you're letting everybody go. Okay. So your cost will increase because of airborne delay in that case. So we don't want that to happen. We want that to happen less. That's the first phase. The second phase is, oh, Seoul Incheon will have a problem. Everybody wait on the ground for 24 hours. Okay. You will have zero airborne delay, right? You will not have a problem coming into Seoul Incheon. But now you've just given everyone a lot of excess ground delay. Okay. So your cost will also go up. So now how do we get to this middle point, right? Hopefully you're seeing this optimal middle ground where you give the plane just enough ground delay so that when it takes off, it doesn't need to do any more airborne holds and just lands at Seoul. Okay. How do we reach that optimal point? Okay. That's going to be basically the driving motivation for introducing this distributionally robust optimization, because the difficulty of hitting that sweet spot is because you don't know what the capacity will be in the next hour, 2 hours, 3 hours. You want to do fancy machine learning to help you understand what that capacity will be, but machine learning could be wrong. That goes back to the first 10 minutes of this talk. Yes, of course. Yeah, yeah.
Uh, if it is generic, to say that there is a trade-off with ground versus air.
Yes. Yes, there is.
Say one was
Yes, you can think of it that way. Of course, you have to be careful with airborne delay because it is so much more expensive, right? So the total cost is going to be weighted differently. And the question here is exactly you don't want to give too little ground delays because then your costs will blow up because of airborne delays. You don't want to give too much ground delays. Sorry, you don't want to give too little ground delays because your airborne delays will go up. So your total cost goes up. You don't want to give excessively long ground delays because yes, you've saved on airborne delays, but then you have excessive ground delays now, right? So now how do we hit that optimal? Yeah, and everybody else should also feel free to. This is the small enough group that we can have just a discussion, facilitated by my slides, basically. Um, okay, well, so we can't do any of this without at least some math. So we have to bring in a little bit of formalisms here. So um, I like looking a lot at these discrete kind of scheduling problems. This is basically a delay allocation or a scheduling problem where my decisions are all going to be binary decisions. One, if I allow aircraft I to land in time period T, and zero is no, I'm not going to allow you to land at this time. So this forms the basic framework of what's called the deterministic single airport ground holding problem. And the picture I want you to have in mind is this. You have one airport, just one. You only care about arrivals into this one airport. You have flights that want to land at this airport at a scheduled time. You have finite capacity at the airport per time period. How do you, with the least amount of pain, let everyone land without exceeding the capacity of the airport? So how do you formulate that as an optimization problem? Well, you want to minimize, if I can find my pointer. Okay, you want to minimize the total cost across all flights and across all time period. And this is basically if a flight was supposed to land at 4 p.m. and it lands at 5 p.m., then you've incurred 1 hour of delay and you multiply that by $1 per delay minute value, let's say. Okay. It's a linear cost function. It's nice, it's not very complex of a cost function. Also, very nice. I mean, this is basically a binary linear program. Okay. So you have all binary decision variables. You have nice linear constraints as well, right? So what is this constraint? This is the main constraint that we're going to pay attention to, which is the number of yes you can land at every time. For each time period, the number of yes that you've said must be less than or equal to the capacity of the airport. Okay. And then what is the second constraint? Well, the second constraint, computers and optimization solvers, they want to please you. Okay. They're very clever. They want to make you happy. If you don't have the second constraint, this problem, if you try to solve it, it'll say, well, you never told me that anybody has to land. So it will give you the trivial solution of zero cost because all of the x's stay zero, all of your constraints are satisfied, and your objective function is minimized at zero. But that's a trivial solution. Okay. So this constraint says for every aircraft, at some point in time, you have to let it land. Okay. So this is the basic vanilla version of the single airport ground holding problem. This problem is super easy to solve in Gurobi. You plug it into Gurobi and it will solve it. You can even solve small instances of this by hand. You could, if you only have a couple of flights, you can do a manual branch and bound procedure and you can find the solution to this problem. Not difficult if this M is a number. Okay, so that's why this is the deterministic version, because you're pretending that the capacity is known and it's exactly going to be M of t, right, for at time t. But of course, that's not what we quite have. Okay, our right-hand side is actually uncertain, but it's worse than that. It's distributionally uncertain. And the question is, how do we make a robust decision when we have potential distributional uncertainties going on the right-hand side of this constraint? Okay. Now let's go back to that conversation that we were having about machine learning. Okay. Imagine, again, you have that machine learning model that's giving you a capacity distribution for this airport at some future time, t+1, t+2, and so on. You're worried that that distribution is wrong. You're worried that in practice, it's actually some other distribution. Okay. We're now starting to talk about how close or how far distributions are. If it's close, that means your machine learning model was pretty good. If it's far, that means your machine learning model was either overly pessimistic or overly optimistic or misspecified the family and so on. Okay. But we're starting to need to discuss a notion of distances between probability distributions. Okay. There are many ways of measuring such distances. You can use total variation distance. You can use symmetrized KL divergences. You can even put your probability mass function into a vector, right? So if you have a probability mass function for 100 scenarios, you can construct a 100 by 1 vector where of course all the entries will sum to 1. It's a valid probability mass function. And you can even take two vectors and take the L2 norm of the vectors, right? That'll give you a fair comparison of the how similar or dissimilar it is. But one reason why we often use this kind of two Wasserstein distance, so it looks kind of gross, but basically what this is, it's measuring kind of a correct notion of distance between a distribution and what's going on in sort of, abstract land is you basically have a space, it's a manifold, but you basically have a space where all valid probability distributions on the same support live on that space. Okay. So when you sample a point on the space, you're sampling a valid probability distribution. That space is not necessarily Euclidean. So an L2 norm wouldn't necessarily be the shortest path between 2 points. Okay. It turns out that this Wasserstein distance describes sort of the shortest path between these two distributions. If you don't care about all of that, just know it's just a way to score similarities between distributions. You'll get a positive. This is actually a valid norm. So you can check all the norm rules, right? It's non-negative, it satisfies the triangular inequality, etc. So this is a valid norm for this space. It essentially becomes a geodesic, right? It's some curve on your manifold space. The other way, so if people have looked into optimal transport, what this is essentially if you imagine two probability distributions and you move mass from one distribution to the other distribution, this is basically the cheapest way of moving mass. Okay. Earth mover distance is also what this is called, basically. Of course, now imagine that your machine learning gave you a distribution p hat. You're interested in optimizing with respects to any distribution that could be within some epsilon neighborhood of your p hat distribution. This is basically you using epsilon as a way to quantify how unsure you are of the correctness of your machine learning output. If epsilon is very small, you're looking at a small neighborhood around your machine learning distribution. If epsilon is very big, you're looking at a bigger neighborhood instead. Okay. Visually, imagine again, so your machine learning gives you this. You're going to blow up a neighborhood of size epsilon around that machine learning distribution, and you're interested in making a cautiously optimal decision against a distribution that gives you the worst case cost. So you're saying, all right, machine learning might be a little bit off. I would like to still make an optimal decision if in practice it turns out that it's some other distribution that better describes the situation, and I would want to make decisions against that distribution. So if you want more visualizations that are not just, so this is basically a cartoon picture that I drew. Um, you can actually plot. So let's say you generate a Gaussian centered at 20. This is your p hat distribution. You can generate, right? You can randomly generate other Gaussians, right? So randomly sample your mean and your standard deviation parameters, right? And your variance parameters. And then you can accept or reject it if it's within some arbitrary. So I'm just using this as a visualization. Okay. So I just had my PhD student generate a bunch of random Gaussians and be like, plot it if this Gaussian is within 0.005 in Wasserstein norm to the red distribution. Okay. So this is a sampling of other Gaussians that live within a 0.005 Wasserstein norm to p hat. But of course, there's no reason that this has to just be Gaussians, right? There's an infinite number of parametric and non-parametric distributions that live within this Wasserstein ambiguity set as well. Okay. I mean, this is particularly interesting to me as an air transport modeler because again, if we take queuing theory as an example, if you've ever worked with like Markovian queues, for example, and you start chaining queues together, you'll get these gamma distributions and Erlang distributions that pop up. Okay, so it's nice to know that we can capture capacities that are not just Gaussian. So if the worst case capacity distribution was some other bimodal or whatever distribution, as long as it's a valid probability distribution, it's fine. It's in the ambiguity set. So now we begin to actually dive into the distributionally robust version of this problem. Note that this essentially becomes a two-stage stochastic program. Okay, so again, remember what I said about cautiously optimal. The cautious part is this part in here, right? This is basically saying, I would still like to optimize. I want to minimize the delay cost, but I want to be sure that if I found the distribution in my ambiguity set that has the worst case expected cost, that I still am optimal against that worst case. Okay. And by the way, this is where I should point out, we have a preprint on arXiv. Please look at that if you want details, because of the time, I will give you just the high level ingredients of what we've done. But go look at the paper. All right, so basically, yes, we have a departure capacity and we have an arrival capacity. Basically, we are now looking at a network of airports. You cannot just think about arrivals because planes also depart from that airport to other airports. So we have to expand this to both a departure and an arrival capacity. And this, as I said, two-stage problem. You want to minimize the expected waiting times across whatever the worst case distribution is in your ambiguity set. Okay. If you took this and put it into Gurobi, it will not solve. Okay, this is not a tractable formulation. So the rest of this talk will be all about how we actually solve this problem. Okay. The first way to do it, which is to reformulate this problem into a deterministic mixed integer linear program, which you can do, and we give you the proof of how you do it in the paper. So you can rewrite that two-stage stochastic optimization problem as a single-stage deterministic mixed integer linear program, which is great because you can actually plug this directly into Gurobi and it'll solve. All right, end of story. We'll talk about the results real quick, and maybe I'll move away for a second, just like so. I'll be obviously it's not meaningless, right? There's some dirty laundry here. But if you solve this problem for a fixed epsilon size, you get 1 point on this orange. Let's talk about interpreting this for a second. So the y-axis, you can basically think of it as the dollars it costs the airlines if you implement a particular delay solution. So of course you want this to be low. The lower the better. The green line is what happens if you use deterministic. If you basically pretend that the airport capacity are the that's what you get as the optimal solution, the cost of the objective function value of the optimal solution. If you use stochastic optimization and you say, okay, actually the capacities are not deterministic, it's a distribution, and I'm going to minimize the expected cost, you get the blue line. And this gap is what's called the value of the stochastic solution. It's the benefit that you get for incorporating information about stochastics. Now let's sorry, in terms of bullet. Correct. Usually you do better because you're accounting for scenarios that could be worse, you can plan for scenarios better, right? You have a distribution over the class. What is very interesting is this orange line. So this orange line is the outcome of the distributionally robust optimization as a function of the size of the ball. So when the ball is of size 0, there's only one distribution in the ball, and that's just the original machine learning distribution. So it turns out that stochastic optimization is the same thing as BRO with a size 0 n. Because we're just optimizing over the same distribution for both stochastic optimization and. But as you expand the ball, you see that the cost decreases. Where is this cost decrease coming from? This is the cost decrease that you get because basically for this data, this is using Bldg data in 2019 across the whole US. On this day, if you expand your ambiguity set, you're capturing distributions that more resemble what actually happened on that day. And you are proactively assigning ground delays to flights that would have occurred earlier. That's where this cost decreases. It's basically the machine learning was a little bit overly optimistic. The actual conditions were a little bit worse than what it predicted. So as you expand this ball, you're capturing worse distributions that you're optimizing against. And so you tend to behave a little bit more conservative. And that's good, because here, that's good because you're avoiding all this airborne. So that's why the cost up to a point. Okay, so after this point, what happens? The cost starts increasing again. Why? Because now your ball is so big that you're improving distributions that are more pessimistic than actually what happened. So now you're starting to become overly conservative. And your cost goes up again because you're assigning extra ground delays. So this is cost mitigation from changing airport delays into ground delays. And this is cost incur, like you incur cost because you're assigning excess ground. This is great. Now you can say, oh, good, you have a nice model that you can get a much better solution if you kind of can find the right epsilon size. Okay, now let's go back to the third one. So remember what I said, you solve this once and you get 1 point on the origin. Because you solve this problem for a single fixed epsilon size. This problem on my student's laptop takes about 2 to 3 hours. Which means that every single point on this curve takes 2 to 3 hours to compute. Which is very challenging because how am I supposed to find the optimal epsilon if it takes me 2 to 3 hours? And remember, I'm making decisions usually for a 2 2 to 6 hour look ahead. How the heck can I justify a 2 to 3 hour evaluation cost? This is very expensive. So, me and my PhD student who led this project, we first said, oh, maybe we can prove something about the monotonicity of this cost function. And so if you can prove that, then the moment it starts going up, we can just stop searching. Right? We can say, well, it's just going to keep going up, and so we can stop. Unfortunately, these cost functions are not monotonic. In fact, so if you go to the paper, you'll see many examples, numerical examples, that, well, I mean, to count it, to disprove something, you just need one example. We found multiple, like there's multiple examples where it'll like go up and then like a little bit of a dip, and then, right? So you can't really do it like it doesn't look like there's going to be eventually we expect the other. Yes, yeah, in the expected cost. So basically, this cost. I was thinking of other. Even those. So I'm not talking about convexity here, right? I'm talking about what is the will this cost monotonically increase convexity? And that's kind of difficult to wrap your mind around. It's basically you're expanding this ball and it's interacting with this cost function. So we couldn't find anything in the literature. What is that? They were someone else already proved the math. We couldn't find it. And then we couldn't prove it ourselves either. Well, we were pretty sure there's no proof because we saw a counter. so then we said, okay, we're engineers. Why don't we just try to solve this problem faster? Let's just talk about how do we actually solve this problem. So this is where I think it's very exciting. My student basically developed a two-phase approximation algorithm that basically, instead of taking 2 to 3 hours, it now takes about 4 to 5 minutes. So a pretty nice speed. So how do we do this? The algorithm basically works in two phases. The first phase is you are basically trying to find better and better and better solutions. You're trying to find better and better and better ways of cutting the feasible space. And then the second thing is basically making sure that all of your decision variables still end up being integer decision. I'll walk you through again the high level of this concept. The couple of key steps that you have to do. Remember, so what's tricky about this problem? The tricky part is this inner maximization. This is the hard part. So step number 1 is to actually take this inner problem and perform a primal dual principle. This is actually pretty scale. This is actually very scale. You would learn this in the first course of a linear programming. How to take a primal formulation and turn it into. So this is critical, but this is not null. It's just a primal dual transformation. The first key insight was recognizing that this problem can actually be rewritten as a unconstrained maximization problem. So we have a proof for this arrow. This arrow is not obvious. First key step was realizing that we write this as unconstrained maximization. Doesn't mean that it's easier to solve. However, that's where sort of the second key point comes in, which is if you're looking at a positive epsilon, it turns out that, so this is the size. It turns out that the optimal solution to this unconstrained problem is guaranteed to be found in this bounded, which is super nice because we all know how to search for a value in an integer. Bisections. golden ratios. Right? You're gonna do a lot of search techniques. So you've now collapsed actually a difficult problem into a simple bisection solution. So this is actually the key anchor for our approximation problem. Set up a scale. It's a scale. Yeah, it's a scalar. So this, it turns out that this all this becomes is a single dimensional. This is where most of the speed up comes. Is instead of solving a nasty, fully written out inner maximization, you reduce this to just a search over a. I mean, it's a search over. I mean, this would be like 0, 4 or something, right? This is just a chunk of the number. So this really is, because I want to leave some time for questions. So what I'm going to skip, okay, so this looks complicated, but if you really stare at this is just a bisection subdown. If you really stare at this, what I'm going to skip though is after you solve this, remember, you have a solution to the dual. Don't have a solution to the final. So you have to do what's called a you have to do a primal recovery step. Basically, how do you take the dual solution down and then chuck it back into? I won't go through this because it's not very exciting. But essentially, we then prove that actually you can do this primal recovery perfectly, so that there's no gap. Anyways, read about it. I want to do so. Okay, so the numerical results. If you remember, so this problem, right? So this is not a. By the way, this is not an approximation. This is actually a exact reformulation. This is no approximations here. Exact reformulation. If you solve this exact reformulation, you will get the column of numbers that's highlighted in red. So each row here is a different size of your ambiguity set. And the red column is you can think of this as the ground. This is the true answer. The blue is what our approximation algorithm gives you. So you of course want the blue and the red to be close, right? Otherwise, why are you doing stuff? So as you can see, the gap is very. The blue and the red are pretty close. Most important, to get a single row using the convective formulation, it takes about 8,000 to 7,000 to 8,000 seconds. Right? This is, if you do the math, this is 2 to 3 hours. That's really 2 to 3 hours. Whereas if you do our approximation algorithm, the times are much small. Okay, in the order of a couple of minutes instead of a couple of hours. And we're very excited for this because, as far as we can tell, this is a novel way of solving a general DRO MILP problem. There's nothing in the primal recovery and nothing in this proof that relies on like a particular structure of the airport route. It's generic to a distribution robust basic structure, which is very nice. So we're looking to actually. So of course, we've written this. It's in review, but we're really looking to. This is where I think there might be some interesting collaborative opportunities, because people have been starting to use DRO in like robotics, or have been doing like distributionally robust control, all that stuff. We're wondering if this algorithm can prove its value elsewhere. Because right now we're very fixated on airports and what I want to conclude, okay, well, actually, maybe I should talk about this. So, what is the value of doing TO? This basically is what this slide is. Just pay attention to this part. This is the part that I reached the most. You can interpret everything else else. So this is for 2019, June 16, and this says, what if your machine learning was off by 10%, 20%, 30%, 40%, 50%? What you have here is the improvement in cost between stochastic optimization and DRO. So clearly, if your machine learning is not that bad, like it's only off by 10%, you really don't get that much benefit. You only start seeing benefits if your machine learning is wrong for that, for the capacity predictions on that. Yeah. And we were happy with these numbers because remember, this is telling you that you have a 5.7% improvement in your objective function value. Your objective function value is literally $1. It's this airline paid $3 million because of extra delays. A 5%, 10% reduction of cost for airlines who will invest in like a new revenue management system that gives them a 1 to 2% improvement in revenue. This is significant cost reductions for an airline on their worst days of operation. But the question is, when would machine learning be off? Like when, this seems like a pretty poorly trained machine learning algorithm. And that's really what I wanted to do. As we all hopefully are as we all know, machine learning, you need data. And you need good training data to train a good model. If you have things like climate change that's making your storm more severe, or like, sometimes in the US it's so hot that it's starting to delay aircraft. So, if the air temperature is too hot, that changes the air density, which means the airplane needs a longer runway to take off on, so on and so forth. Because of climate change, we're starting to see this used to happen even back in the early 2000s. So we don't really have a lot of data for these kind of things. So I think that's kind of what I wanted to prove with on the aviation side, which is a lot of people, the US Federal Aviation Administration, Eurocontrol, so on, they're very excited about using to help them. What I want to leave y'all with is, if you trust your machine learning models, don't do just do stochastic optimization. Think it's a good output. Use stochastic optimization. You're probably, but on these weird situations where you don't have a lot of training data, like don't have good confidence that your model is converged, maybe it's worthwhile bringing in some robustness into how you make decisions, if you're making decisions against the output of some foundation service. Oh, yeah, this is basically that. This is basically what I said, but it didn't work. So in the US, we're very, very interested in bringing in AI/ML, but given that clinicians can have this uncertainty, how do you make decisions that are robust? And so DRO might be a good answer for when we are not social the good machine learning. Or that. Oh, yeah. So this is basically this entire project was funded by a NASA Center for Air Transport Resilience. Something else that I maybe want to leave with, given that I think you all are there to you're in the aerospace. It is so important that we don't just stay in our labs. I think it's super important that we engage with the people in real life who's trying to make this up. At the end of the day, we're engineers, we're not mathematicians. At least that's my challenge. So I'm really happy that this project allows me to interact with airline, airports. So I get to talk to them about these DRO stuff and what we're doing. I want to make sure it captures their concerns. I think that's super. And then finally, I'm really just a spokesperson. All of the work is basically done by Hutchin. Student, and we've worked quite a bit with Professor Alex, is professor in business at the university. Okay. Thank you so much. I believe there are. Yes. Happy to discuss. Yes, please. Oh, good. No, listen. I have such a big pet peeve when I'm like in a talk, like listening to a talk, and then slide 2 is like 17. What's happening? What's my true belief is I'm not here to necessarily teach you the content. I'm here to make you understand what was our motivation and our research problem, and you can go home and right like the paper. Like I cannot describe that paper in an hour. There's no way. There's like 6 proofs. There's like too much things. I really believe these talks is a way of conversing and letting you know kind of intuitively at a high level what my research is about. And now you can ask questions, and of course, okay, sorry, what was your
Yeah, so I like to really help me. My question. I wonder how this euro can be so actually help air traffic managers or airlines decide how much ground they much airport. For example, if I have a distribution model and I know that I cannot spend, so I how can I get offline? Can I get like sure.
Yeah, that's a good question. So actually, I think something that I didn't talk about is it's actually kind of it's difficult to know if your machine learning is misbehaving today. Right. So actually, that's a question that I did not tackle. So you first have to have a way of knowing or suspecting that for today, your machine learning predictions might not be very good. Maybe the confidence interval is very big, right? Maybe there are ways of that, but if you suspect that the machine learning model is off, then what you would do is you would run this DRO across different epsilon values and then say, okay, do I want to be super conservative or not super conservative? So you would then pick an epsilon, run it, and the output is actually a schedule. Right? Remember, the decision variable says, do I let this flight go at this time? So the output of this is very implementable. Right? The output of this is precisely like Korean Air 123, you get 60 minutes of delay. China Eastern, you get 40 minutes of delay. Right? That's the output of this optimization. The two important questions is how do I know if my machine learning is bad for this thing? That's important. I actually don't talk about that in this talk because I don't know what the answer is. The second question is how conservative or not conservative do you want to be? And that is a decision for the air traffic manager. Right? So today, air traffic managers are doing this just without the math, right? They're like, I think today will be kind of bad. I'm going to be more conservative today, right? And sometimes they're right, sometimes they're wrong. But now we actually have a way of taking that like gut feeling that they have and actually putting some numbers to that. So, because I think that's still this is not like you cannot just take this and give it to an aircraft. This is like still this is very much research. Lots of other sort of practical considerations that I have. Thank you for the question. Other questions? Comments? Yes.
Thank you for her presentation. My question is that the problem formulated in this work is to deal capacity as one-dimensional problem. But I think maybe it can be that dimensional problem time of capacity of region one and region two, and it is still work.
Yes. Yes. So that's a great question. So if you have 30 airports, we make 60 capacity distributions, right? 30 arrival capacity distributions and 30 departure capacity distributions, each of which is a single dimensional, it's one random variable. We assume, and this is a very bad assumption, if you ask me, but we had to do it because we actually don't know how to solve this problem otherwise. We assume that the capacity between airports are independent, which is a really bad assumption, right? So for example, it's very obvious, even if you look at Seoul. There is no way that the capacity at Gimpo and the capacity at Incheon are independent. If there's a weather problem at Incheon, it probably is going to happen in Gimpo. However, if you want to talk about joints distribution, so that's kind of what you're moving towards, right? Like an n-dimensional joints distribution over n airports that are correlated. Even if you want to talk about the basic, what's sort of the easiest correlation structure you can think of? Linear correlation, right? Pearson correlation. We actually, like, we found it very difficult to deal with this high dimension of, like, I mean, we have to be careful. This problem is high dimensional because we have hundreds of thousands of decision variables, we have hundreds of thousands of constraints and so on. But the probability distribution is not like a nth dimensional probability distribution. It's just a single right variable. I actually don't know. Like the math is very complicated if we move into like a joint n-dimensional distribution. We don't solve it. Open question. Maybe one of you can solve that. I'm not. Yeah, it's very challenging to talk about joints distributions across multiple elements that are correlated with. I mean, most of the time, right? I mean, what's the easiest case? Independent and identically distributed. That's the easiest case, right? You assume independence. So it's a lot of things become harder once you. So that was a very non-answer, but basically my answer was we don't. Other questions? Yeah, of course.
Yeah, so what I thought of the number, a goal that able to once again
yeah.
And also once again, like for example, you have to input whether with information. Is it also once again those
that's a great question. So I'm kind of assuming that if those inputs are uncertain or very uncertain, then your machine learning output might be worse. So we sort of scope that out, right? We only look at what came out of machine learning, right? You could have fed it garbage. You could have fed it a really nice thing. I don't know. I'm just looking at the output. And my question is, can I make a decision that's robust against that output? If you are interested in looking at the input uncertainty, that's obviously very important for making a better machine learning, right? Like if you want your machine learning to be better in the first place, and listen, if you this also becomes a question of where do you put your efforts, right? Do you put your efforts into making the machine learning better, or do you put your efforts into mitigating issues with the machine learning out? And that's what, so this is more about we're dealt the hands that were dealt from the machine learning output. How do we make a decision given that this hand could be bad? Your question would be more, how do we make sure that the hands that were dealt is good to begin by maybe reducing some of the input? So it's just different, looking at different phases. Does that make sense? Yeah.
Slide with the
this one? Sorry, which slide?
with the curve.
Oh, yes, yes, yeah, yeah. This one.
Yeah.
Yeah, yeah.
So what I understand is that we try to prove the original might have I did really bad.
Well, yeah, we didn't usually start because we saw. But yeah.
But in my guess, I can guess that there must be some kind of relationship that must be as well after bigger one the value of it. I can guess that must but no. Yeah.
Yeah, so is there a chop?
There should be
Oh, I see it. Okay. So the sort of the picture that I would have in my mind is, you have some, right, you have some space, and you have your p-hat distribution, and you are basically expanding, right, this epsilon ball. So so essentially how we attempted to start this proof is, so you have some delta change in the epsilon, right? And you're interested in observing if this delta change in epsilon, it can we say something about this epsilon? If this is a positive delta change in epsilon, can you say something about the change in the objective function value, right? But the objective function, so the objective function is like this complicated, so it's for us, let's say U and B. So we were making this, it was this min over U and B's subject to basically a cost plus a max over some expected cost, right? So this cost function is not like you basically have to reason about all the new, so basically all the new distributions that appear after you make the delta epsilon. You have to evaluate that against this distribution, against this objective function, because now this is basically what, so this is always with respect to some p, and this p is now has this additional chunk of distribution. So the issue is, just because you expand this epsilon and you include more distributions doesn't mean that this worst case cost will always go up under this objective function. If it's a simpler objective, so if you, I don't know if you've heard about for example, the Newsminder problem. So in the distributionally robust Newsminder problem, the cost actually does look something like this, and this is one. Absolutely. But that's because the newspaper problem had a very simple objective. This is a much more complicated. Actually, in fact, someone asked me, well, why don't you just write in the new optimization problem where the decision variable is like, why don't you just write like, you know, a larger optimization problem where you are minimizing also with respect to the epsilon value. And then I said, great, you solved it. I don't know how to solve this, right? Like this is like, I don't even, this has like gone way outside of the realm of like known formulations that we have. This is not even this is a continuous optimization problem over a manifold problem. I don't really know how to solve it. So we gave up on this monotonicity thing very. I just wanted to kind of mention it because, you know, looking at this, you might think it is monotopic, but actually, like, first of all, this is not even evaluating it at different. So maybe it, like, right, there could be little jitters. I mean, a proof requires sort of this absolute certainty, but yeah. So unfortunately, it's not. Yeah, we could find sort of how you show monotonicity. But I was just wondering that. Give us. Yeah, no. If you can, so if you can help me understand anything about this, so like this is a very complex object actually, right? Because it's a complicated objective function interacting with this epsilon parameter that's controlling the size of the end. If you can tell me, we remember all of my talk from this point on was just about how to solve faster. We didn't actually talk about anything in terms of like a more theoretical characterization of this cost function, stuff like that. Not because we're not interested, but just because we were not that good at the math. And we sort of didn't really know what to do next. Okay. So please, yeah, I mean, I would love, this is like, I'm very interested in kind of trying to dive deeper into the abstract part of this. That would be great. We just ended up spending our time slightly more practically. So, also computer. Oh no, thank you. Oh yeah, question. Go for it. Yeah, I got a lot of questions. Thank you. Yeah. But I think it's interesting to see that Trent is so. So you try to show how the outer set works out of distribution depends on the size of ambiguity set for the distribution. First of all, is there been any other study dealing with this how ambiguity set? Yeah, the choice of set. Yeah, I think so. DRO is a pretty active topic right now within kind of the research, operations research community. I think some people have tried to look at this characterization of epsilon and the objective functions and the objective function value, but we couldn't find anything that was directly helpful for us for this one. But yeah, there are like so there's two. There's Professor Wei Jiang at Michigan is doing a lot of DRO work, and so is Professor Daniel Kuhn at EPFL over in Switzerland. Is doing a lot of work. So I think I would basically go to their group and go see their papers and maybe papers that cited there to see what sort of the cutting it. Honestly, I do think we made a really novel contribution in terms of the algorithm. We really haven't made a lot of contributions in like the theory of DRO, right? Yeah. So again, our focus was a little bit more applied, right? It was like, how do we use this in air traffic setting? Along the way, we found a really cool approximation algorithm that runs a lot faster. But at the end of the day, I am an air transportation person, not an OR person.
I believe where in UK, where in UK, there was a project group.
Yes. Yeah.
Yeah. Yeah, which that's the first way it's a digital twin. The proper position was would it be for the entire airspace of the
I think it was just the UK airspace.
but as far as I know, Korea doesn't have any such learned probabilistic now, my question is, I believe this will work in well, it has some implications on when to it has some implications on the data from the machine learners side.
Yes.
From the machine learners perspective, I need to make a decision how many data points we should get it to build a good enough
good model.
Yeah, good enough.
Yes.
And well, likewise, when to stop, right? When to pour in more data. Do you have any thoughts on that? What's your
Yeah, I'm very familiar with Project Bluebird. Spent many hours over beer this last slide deck actually. Really good people working on that project. I would love to be able to draw connections between this distribution and robust optimization work and what it can tell us about the value of training and the value of spending compute time to train further. I do think there are connections to be made. I don't know if we necessarily need this level of machinery, right? I mean, this is pretty overkill if your machine learning model never is really that subject distribution shifts or context shifts and stuff like that. This is pretty much I would say this. But the reason why I think this could be interesting for air traffic is because air traffic suffers from a natural data imbalance, right? So like most of the time, demand capacity is fine. Like in the US, 80% of the days are perfectly fine and there's no problem, no delays. But the 20% is really bad, and we want to help the 20% of days, but by definition, they're not a lot of data. So what that implies for machine learning and AI usage is like anytime anyone shows me something that's ML related for air traffic, air transportation, my question always goes like, how do you know that this is sufficiently trained, that this is comprehensive? DRO is almost our answer to the second question that comes after that, which is okay, but then what do we do operationally? But there's a question that comes before it, which is how do we make machine learning better? I think that's a separate question. But yeah, this is an overly general statement, but I think the US tend to be a little bit more cautious when it comes to integrating AI into like something like air traffic. Asia might not be, right? Like Asia might be a little bit more open to say like, can we how far can we push the boundaries? Oh, that's you. Oh, that's my own perception. I don't know if that's true or not, but I just feel like there's sort of a more forward-leaning technological mindset. But I could be wrong. Actually, for example, something that I didn't even really talk about is a nice byproduct of our approximation algorithm is that you actually get, like, you can see what is the worst case distribution. So you can actually construct worst case distribution. The air traffic managers I've talked to are very interested because they want to see if that visualization looks like their gut feelings or statements that they've ever experienced. I think that's the kinds of conversations that we need to have to make people more comfortable with. Like, I would never give this presentation to an air traffic manager or an air traffic because they're not researchers, not mathematicians. They're going to be like, I don't understand any of this. Just tell me what is the value to me, like what is the benefit of all of this? But yeah, no, I want to talk to the Project Bluebird guys because they've never seen this work, and I think if that's going to be the first worldwide, like if Project Bluebird, if it gets operationalized, if that's going to be the very first time in the world where we actually bring in AI into the air traffic control and air traffic management loop, one, that's very exciting, and two, I want to be there for like, what if things go wrong? And you could actually do much better than what machine learning naively tells you.
Great. So thank you very much.
Yeah.
Really, really exciting. That's thank you very much.